On the left-hand side, we have the reactants. This is the yield sign. And on the right-hand side, we have the products. The equation here is balanced, but you should always make sure that you have a balanced equation. Now, how do we read this? 4 moles of carbon reacts with 1 mole of sulfur, S8, to yield 4 moles of CS2. You look at the question, it's saying that there's 2.1 mole of S8. And we want to know how many mole of CS2 are produced. So when you get a question like this, where they only ask you about one of the reactants, they don't tell us anything about the carbon. There are two terms we need to know here. This sulfur is the limiting reactant. In some books, you'll see limiting reagent. It's the same thing. They don't tell us anything about the carbon, so right there we just assume that this is the excess reactant. The reaction is limited to this 2.1 moles of sulfur. So the amount of product we get is just dependent on this number right here. There's going to be carbon left over. Carbon will react, but this is not what's going to limit the amount of product. We want to convert the moles here to the moles here. And we do that by knowing the mole ratio. The mole ratio of carbon disulfide to sulfur is just 4 to 1. So watch how easy this is. 2.1 mole of S8. We want to convert to the mole of CS2. Let's cancel the mole of S8. So when you see this mole to mole ratio right here of carbon disulfide and sulfur, that comes right from our mole to mole ratio. For every 1 mole of sulfur that reacts, you will always produce exactly 4 moles of CS2. And that's it. If you understand this step right here, then you can do any stoichiometry problem. So let me pause there. Two moles of O2 and we want to know from the 2 moles of O2 how much NO2 is being produced, how many moles of NO2. So just from this question, as we saw a second ago, I can just assume that this is our limiting reactant because that's all I'm worried about. The hydrazine, this will be considered the excess. So the hydrazine will react with O2, but we just assume that this is excess because all I'm worried about are these 2 moles of the O2. Okay, so let's do it. From unit of moles, we use the mole to mole ratio. Let's convert this to the mole of NO2 because that's what the question's asking for. And let's cancel the mole of O2. So when you see the mole to mole ratio, that comes from the balanced equation. For every 3 moles of O2 that react, you will always produce exactly 2 moles. Our answer should be 1 significant figure. So let's check that. 2 times 2 is 4. 4/3 is going to be 1.3333, whatever. But the answer should be 1 sig fig. So this is interesting. At least to one significant figure that we're certain of, this will be 1 mole of NO2. We're doing the exact same problem. We want to find the amount of product, but instead of moles, they give us the grams, and we want to find the grams. Couple things here. Number one, they tell us the limiting reactant. The one that they don't give us, the other reactant, of course, will be excess. So we don't have to worry about finding the excess. So we just assume that it's this one because they don't tell us anything about chlorine. The rules of stoichiometry don't change. In order to find this relationship, we need units of moles. We're going to go from our grams of CS2. Let's convert to the mole of CS2. And how do we convert grams to moles? It's called the molar mass. Then we can convert to moles of anything, whatever I want to look for. In this case, we're going to go to mole of the disulfur dichloride. They're asking for the answer in grams, so of course we can convert moles to grams of disulfur dichloride and use the molar mass to convert the moles to grams. 5.80 gram CS2 multiplied by a ratio. We want to convert to mole of CS2 and cancel the gram of CS2. The molar mass, remember, it's 1 carbon, so molar mass for carbon, for 1 carbon, plus 2 times the sulfur. Now, sulfur on my table is 32.07. So to 2 decimal places, that's good enough for our calculations. 76.15 for the molar mass. The mole to mole ratio, again, we're looking at our balanced equation. Now, this is pretty convenient. This is just 1 to 1. For every 1 mole of CS2 that reacts, you will always produce 1 mole of the S2Cl2. Right here at the end, we've already solved the answer, but they're not asking for moles of product. They're asking for the grams of product. So right here, S2Cl2. Here we have the molar mass for 2 chlorines plus 2 sulfurs. Right here, we start with 3 sig figs, so our answer should have 3 sig figs. So I'll answer 10.3. A little bit different. In the last examples that we've done 3 examples so far, and in each example, we converted a reactant to a product. But this question's interesting because it's asking, well, if I start with this amount, how much chlorine do I need to completely react? And by the way, for your engineers, some of you going into chemical or petroleum engineering, this is really a really important stoichiometry problem. So you want to minimize the amount of reactant you use. You don't want anything extra. You don't want to spend your money and buy more than what you really need. You want to spend just the right amount on exactly what you need. So that's part of the cost efficiency for those of you that are going to come across that, and every one of you will come across cost efficiency at some point. So this is actually a very important problem. To find the moles of iron, we divide by the grams of iron, and that comes from the periodic table. This is 55.845, but we'll round to 2 decimal places. That's good enough for our calculations. Now that we have moles of iron, now we can convert to whatever we want. In this case, we're converting to a reactant, mole of chlorine, and cancel the mole of iron. Right here, pretty convenient. This is a simple 1-to-1 ratio. So again, that comes from the balanced equation. We already did it. We found the amount of chlorine in terms of moles. But be careful. Sometimes we ask for moles, sometimes we ask for grams. So in this case, they're asking for the grams of Cl2. I use the molar mass to cancel these units out. Check those units. See how all these units cancel? It all makes sense here. So the final answer is in grams. Chlorine is 2 chlorines, so 70.90. I start with 3 sig figs. My answer will have 3 sig figs. 12.7 grams of Cl2 will completely react with 10 grams of iron. That's the significance here. That's what this number means. This number represents the amount of chlorine that reacts with all of the iron. In our previous questions, they told us, well, this is how much reactant we have, find the product. This is how much reactant we had, find the product. This is how much, where am I? Right here. This is how much reactant we had, find the product. That's interesting. Here, they tell us, well, we have this much reactant of one reactant, and then we have this much of the other. When you get a question like this, you must find the limiting reactant. Sometimes it's called limiting reagent. It means the same thing, limiting reactant or limiting reagent. And they want to know how much is produced. Here's how you find the limiting reactant. Pick one product, just pick one. I'll pick ammonia for this example. I'm just going to pick one. And we're going to do a test. Convert the calcium oxide to ammonia, and let's get an answer. How many moles are produced? In a separate problem or in a separate math equation, I'm going to convert the ammonium chloride to ammonia, and I'm going to get an answer. How many moles are produced? Let's do that, and then we're going to compare the moles. Whichever one produces the fewest is going to be limiting. Test both reactants with one product. I'm going to pick ammonia for this example. Whichever reactant yields the smaller product is limiting. Let's start with 164 gram of calcium oxide. In order to do this conversion, in order to use this ratio, I need to find the number of moles. So let's convert to the mole of calcium oxide. Let's cancel the gram of calcium oxide. Using the molar mass right here, I can convert grams to moles. So we're good here. Now let's convert to one of the products. I'm going to pick ammonia for this example. So notice how I convert to mole of ammonia. Notice how I cancel the mole of the calcium oxide. In this equation, that's already balanced, by the way. So be careful. Make sure the equations are balanced. They're not always going to be balanced. In this case, they balance them for us. The ratio here is just 2 to 1, right there, 2 to 1. I start with 3 sig figs. So my answer here, 5.85 mole of NH3 can be produced from 164 grams of the calcium oxide. We're not done yet. We still have to test the other one. I don't know which one is limiting. I have to do another test. But this is what I know so far. Let's do the next one. 323 grams of the ammonium chloride. Let's convert to the mole of ammonium chloride and cancel the gram of ammonium chloride. The molar mass here, this comes out to 53.5 times. Now this one's a little bit different. The mole to mole ratio here is 2 to 2. So for every 2 moles of ammonium chloride that reacts, you will always produce 2 moles of ammonia. So notice how this cancels here. So the answer here, 6.04 mole of ammonia can be produced from 323 grams of ammonium chloride. Let's draw some conclusions. If I only had 164 grams of calcium oxide, I can produce 5.85 moles of ammonia. If I have 323 grams of ammonium chloride, I can produce 6.04 moles of ammonia. So you can imagine if these two things react, as soon as you get to the smaller number, then the 164 grams of calcium oxide has now run out. The calcium oxide that produces the fewest amount is the limiting reactant. Now, notice here, the ammonium chloride can give you more ammonia, but we never get to this number here because as soon as we get to the 5.85, then the calcium oxide has run out. So let's draw some conclusions here. 5.85 mole is how much we can get. Calcium oxide is limiting, and the ammonium chloride is the excess. Now that we know that calcium oxide is the limiting reactant, we use the limiting reactant to find everything else. So when they ask us how much water, so watch this, 164 convert to moles. So I'm just copying what I have right here. But now look at this. I'm going to convert to the mole of water and cancel mole of the calcium oxide. So notice here, I've changed what I'm looking for. So 3 sig figs, 2.92 mole of water. We can convert to mole of the calcium chloride. And if you look closely, right, instead of going to water, we can go to calcium chloride. But if you look closely, what do you notice? It's the same ratio, right? So there you go. It's actually the same answer. Right? Notice how nothing changes there. Just this last part right here. I'm going to do the same thing, but I'm going to convert to the mole of ammonium chloride and cancel the mole of the calcium oxide. The ratio here is 2 to 1 from the balanced equation. Yeah, so this is the 5.85. Now, again, these are mole ratios, and we're looking for the number of moles. So it's not surprising, right? I mean, if the mole ratio is 1 to 1, these answers are going to be the same. You see how this mole ratio is 2 to 1. So that's the same thing we did here. So it's the same number of moles. If you're converting to grams, obviously, these all have different molar masses. Um, so that's going to be a little different. These are the moles that are used up. So we can call that consumed. These are how many moles are consumed. But they're asking us how many moles are left over. So we need to know how much we start with. So let me just do this quick calculation, right? Let me find this part right here. So 323 divided by 53.5. These are the number of moles that we start out with 6.04 mole. The ammonium chloride minus 5.85 mole of ammonium chloride used. So that's how much is consumed. And so here's our answer. 0.19 mole NH4Cl remain. That's how much is left over.